Hello everyone. So what we're going to see this week is a bunch of theorems that are quite fundamental to calculus, and that seem pretty obvious at first, but we'll see that they lead to surprising and fascinating consequences. Alright, so the first one we'll see in this video is called the intermediate value theorem. So to explain what it is, let me show you one of the greatest race of all time, namely Usain Bolt 100-meter record from 2009. So let's watch the show.
Schnellste aus den Blöcken, jetzt kommt er und jetzt ist Usain Bolt nicht zu halten, nein, er gewinnt!
That was pretty crazy, pretty unbelievable. 9.58 seconds for 100 meters. That's insane. Alright, but what does it have to do with the intermediate value theorem? Alright, so what Usain Bolt just did here, so he started at time 0 at a position of 0 meters and reached 100 meters in 9.58 seconds. So the intermediate value theorem is very simply telling us the fact that if I pick any distance between 0 and 100 meters, then Usain Bolt must have gone through that point at some time between 0 and 9.58 seconds. That's pretty obvious, right? Of course, if I choose a distance, say 50 meters, then yes, Usain Bolt must have run through 50 meters at a certain time. That's almost trivial. But we'll see that, in fact, this very simple fact leads to very surprising and unexpected consequences. Okay, so let me try to understand that mathematically. So if I'm drawing the position function of Usain Bolt as a function of time, so he started at time 0, position 0, he probably went through something like that, reached something like a constant velocity, and then ended up at 100 meters in 9.58 seconds. So the intermediate value theorem is telling me that if I pick any distance here between 0 and 100 meters, say 50 meters, then Usain Bolt must have gone through that distance at a certain time between 0 and 9.58 seconds. That's pretty simple. Okay, so let me just formalize that. So the intermediate value theorem states that a continuous function, any continuous functions, takes on every intermediate value between the function values f of a and f of b. So in my example here, a was 0 and b was 9.58. F of a was the position at 0, which is just 0, and f of b was 100 meters. So what we're saying here is that the function here, the position function of Usain Bolt, takes any intermediate value between 0 and 100 meters at a time between 0 and 9.58 seconds. So another way of understanding that from the graph point of view is that if I choose any any number here on the y-axis, I can draw a horizontal line, and the function cannot jump over the horizontal line. It has to cross the horizontal line at a certain point. And that's obviously true as long as the function is continuous, which is one of the requirements of the intermediate value theorem. So formally, the intermediate value theorem statement is the following. Let f be a function that is continuous over the interval a to b, and let capital N be any number between f of a and f of b. Then there must exist a number c or a point c between a and b such that the value of the function at c is exactly equal to capital N, and that's got to be true for any capital N between f of a and f of b. Now, the very important point here is that the function must be continuous. If it is not continuous, then this doesn't have to be true. For example, I could draw a function here, something like this, with a jump, and then that is clearly not true because, for example, the function here never actually go through 50 meters between 0 and 9.58. So I cannot conclude the statement of the intermediate value theorem if my function is not continuous. It must be continuous. All right, so that's a simple statement, but we'll see that it leads to very interesting consequences. So first, one thing we can do with the intermediate value theorem is use it to calculate the zeros or the roots of a function. So we know how to find the roots of quadratic polynomials. We have a formula, minus b over 2a plus or minus 1 over 2a square root of b squared minus 4ac. But if I give you a more complicated continuous function or a higher degree polynomial, you don't have such a formula. So the IVT gives you a way of finding or locating roots of polynomials or continuous functions. So how does that go? So let me just give you an example in this video. So let's look at the function x cubed minus x minus 2. How can you locate the roots using the IVT? Well, one thing you can do is pick a number. Suppose x equals to 1 to start with. Then the value of my function at 1 will be, in this case, 1 cubed minus 1 minus 2, which is just minus 2. All right, now let's pick a second number, say x equals to 2. Now the value of my function here will be equal to 2 cubed minus 2 minus 2, which is equal to 4. So what the IVT now tells me is that for any number capital N between minus 2 and 4, there must exist a c between 1 and 2 such that f of c is equal to capital N. In particular, I could choose my capital N to be 0 here, because 0 lies between minus 2 and 4. So IVT here implies that there exists, or there is, a c between 1 and 2, such that it is a 0 of my function, namely f of c is equal to 0. So I don't know exactly what is the value of the root, but I know that it lies somewhere between 1 and 2, which is already a quite interesting statement. But now I can keep going, right? I can pick the midpoint of my interval here, so that would be 1.5, and I can evaluate the value of my function at 1.5, and if I'm not mistaken, I think you get minus 0.125 in this case. Now this is still negative here, so and f of 2 is still 4, so 0 lies between minus 0.125 and 4, so IVT now implies, again, that there is a c, but now between 1.5 and 2, such that f of c is 0. I still don't know exactly where it is, but now I've made the intervals smaller. I know it's now between 1.5 and 2. And of course, I can keep going like that, do it as many times as I want, and I get a better and better approximation of the zeros of my function. Now, this method is something called the bisection method. It's a very effective way of finding roots of continuous functions, and you can implement that numerically on a computer, and then you can find better and better approximations of the roots. So we'll study that in more detail in class. That was just to give you an idea of how you can use the IVT to solve problems. All right, so let me end this video with a really interesting question. So consider the Earth, our planet, and think of the equator, which is, of course, the equator, so one of the great circles on the Earth. Now, let me ask you the following question. So, of course, you have a temperature distribution everywhere on the Earth. So everywhere on the Earth has a certain temperature at a certain time of day. Now, is it true that for any given time of the day, for any day of the year, there are two diametrically opposite, so a point here, say, another one on the other side of the Earth, which are such that they have the exact same temperature? That sounds totally crazy, right? I'm telling you that at any given time of the day, you can find 2 points on both sides of the Earth that have the exact same temperature. Well, think about it. We'll come back to that in class.